I'm Jeremy, and my co-author is here as well. It's Mashbat. We're both from UNSW Sydney. I'm a PhD student, and Mashbat is a postdoc. Okay, so I'll start off the talk with a little toy example. So we have three friends represented here by these clowns. They want to pick two activities that they're going to do together. So let's imagine that each friend is interested in really only one of the activities, and that's represented by the circle corresponding to their color. We want to figure out how can we pick two activities in a fair way. So it seems that it's impossible since one friend will be left with no activity that they like, right? So how do we usually resolve this problem in practice? Well, we would draw straws or roll a three-sided die, or in some fashion, randomize. And why is this fair? It's fair in expectation. And so it's fair ex ante. So to summarize what we want to do in this paper in a more broad way is to look at committee voting, where we have to select more than one alternative, and we want to study ex ante fairness in the case where voters have dichotomous preferences, so where they just have 0, 1 utilities for each candidate. Okay, so I'll introduce the model of probabilistic committee voting. I'll then introduce the fairness property and characterize it that we study in this paper, and I'll explore the compatibility of that property with some various other desiderata in the setting. Okay, so just using our example, this is the classic approval-based committee voting model. We have a set of voters, N, that were our three friends in the example. We have a set of candidates, C, that were the activities. And each voter then approves of some subset of candidates, denoted AI for voter I. And we would like to select a subset of candidates size K. So for our example, K was 2. Okay, so now we want to study probabilistic committee voting in this paper. So we're going to refer to what's normally just a committee as an integral committee. That's a subset of size K. So for example, we might say these two candidates, movie and gambling. And a lottery then is a probability distribution over integral committees. So for example, we might place 1/2 probability on that integral committee we just had, and another 1/2 probability on the integral committee that selects bowling and movies. Okay, so then a fractional committee is just the fractional relaxation of an integral committee where we have a vector of probabilities for each candidate, and that vector should sum to K. So for example, we have maybe 1/2 probability, 1 probability, and 1/2. So then there's a sort of important correspondence between the lotteries and the fractional committees, namely each lottery corresponds to exactly 1 fractional committee. And we say that it implements that fractional committee, and that is the fractional committee where we place the marginal probability of each candidate being selected in a random sample from the lottery for that candidate. So for example, this fractional committee that we see here is implemented by the lottery that we had before. Or we say it's an implementation of. Okay, so then voter preferences are basically normally just the number of candidates that you approve of in the committee that is selected. So how do we reason about voters' preferences over committees? Well, we'll say that the utility of a voter for a fractional committee is equal to the amount of probability that's allocated to candidates that that voter approves. Why do we do that? Well, this would be their expected utility from any lottery that implements that fractional committee. Okay, so just to remind you, we might say that the blue voter here has 1/2 utility under this fractional committee, which makes sense because any lottery implementing that fractional committee will give that voter 1/2 utility and expectation. Okay, any questions on that? Okay, so we want to study ex ante fairness in this problem. Usually fairness in committee voting focuses on proportional representation. The idea that every subset of voters should receive representation proportional to their size.
Just one clarifying question. The
Yep.
utility is AI intersection the winners, the size.
yes, under an integral committee. And then our for fractional committee, just an expectation. Yeah. Okay, so this is usually studied with the notion of core, which you might know from other settings. In committee voting, existence of the core is major open problem. Its fractional analog, however, is guaranteed to exist, but there's no known polynomial time algorithm for it. So let's just look at fractional core first. And we'll talk a bit more about it in a couple more slides. But fractional core is essentially saying that there should be no group of voters that could choose an alternative committee that is proportional to their size that they all strictly prefer. Okay, so when k equals 1, to maximizing Nash welfare will satisfy fractional core. So if we maximize the product of voters' utilities, we can get fractional core. So we show that this is not the case in probabilistic committee voting, where Nash welfare violates fractional core and actually a weaker property. And so this means that actually we don't really have an explicit algorithm for fractional core in this setting. So to remedy this, there have been a number of properties weaker than fractional core defined based on the notion of fair share that's resulted in these two hierarchies. And our first goal is to define some relaxation of fractional core that unites these two hierarchies of properties and is achievable in polynomial time. Okay, so to define our property, we just want to revisit fractional core, which has a taxation interpretation that kind of helps you understand it, and we can then use that to motivate a new property. So the idea is that the budget of K, or the committee size, is really composed of like a flat tax from every voter of size K over N. Then that money is used to buy candidates, which you can think of as just costing 1. And fractional core just says no group of voters S would prefer to take their tax money and spend it together on some other set of candidates that would all bring them more utility. So we want to use this idea of tax contribution, but what we're going to do is lower bound the amount of tax contribution that is used to buy candidates approved by some voter in S for every group of voters S and N. So more concretely, what we would like to do is the following. We'd like to lower bound the amount of probability allocated to candidates that are approved by someone in S. And we'd like to lower bound that by the total tax contribution of the voters in S. So this would be nice, but unfortunately, it only requires a simple example to show that it's impossible. So if we consider an altered version of our original example, where we have now 2 voters that approve of 1 of the 4 candidates, we need to select 3 candidates. Then it's easy to see that if we consider these 2 voters and call them S, that cardinality S K over N is now 1.5, but they only approve of 1 candidate. So this inequality cannot be satisfied for them because we can't select bowling with probability 1.5. So this gets worse in a way, because even if we add this magenta voter who seemingly isn't problematic with respect to the inequality remains problematic because we now need to select for this group of voters S more than 2. We need to give more than 2 probability to a set of only 2 candidates. So the core issue here is that within any group S, there can be some subset of voters in S where there's a large gap between their total tax contribution and the number of things that they collectively approve, right? So we need to sort of balance this inequality or apply some penalty for each group of voters S. So that corresponds to exactly what I just said, which is this gap between their endowment in a sense and the number of things they approve. And we want to find basically the subset of voters where this is maximized, and then reduce the amount that we're guaranteeing that set of voters S. So then with that, we say that if we can give this inequality for every subset of voters S, then the fractional committee satisfies group resource proportionality. Okay, so that's our property and we'll refer to it as GRP. Okay. Just as another comment, the left-hand side here, you can also think of as basically, if in the lottery interpretation, any lottery implementing this fractional committee would be an expectation containing this number of candidates that someone in S approves. So it also has this expectation interpretation. Okay, so we show that this is indeed stronger than GFS and strong UFS and unites the two hierarchies. And it is a relaxation of fractional core. So then the question is it tractable? Okay, so to answer this question, ooh, that's not pretty. Okay, interesting. Okay. So this is a flow network that was mangled, but I don't think there's any way around that. Okay, so I guess you'll have to use the text and just imagine it. Okay, so we essentially we're creating a network representation of the instance where we have a source, a sink, a layer of nodes for voters, a layer of nodes for candidates, and I'm just gonna draw it really quick. Okay, so source, voters, candidates, sink, okay? Every voter is connected to the source, and we give them K over N capacity to flow to each voter, okay? Then each voter is connected to any candidate that they approve of, only the ones they approve of. We can flow anything here, but each candidate can only flow to the sink with value 1, okay? So in essence, we're kind of capturing this text interpretation. We're saying we're going to give them sort of a budget of K over N. They can flow to any candidate that they approve of. And then from those candidates, we can select them at most 1, right? So this flow network interpretation or this formulation turns out very helpful because it allows us to characterize GRP. So we can say that a fractional committee P satisfies GRP if and only if it essentially element-wise dominates a max flow on the network where we're capturing the flows from each candidate to the sink. So there should be then, right? So there should be some flow, some max flow that where the flows from each candidate to the sink are lower than the probabilities in the fractional committee. Okay, so why is this helpful? First of all, it tells us that GRP can be achieved in polynomial time by simply computing a max flow on the network. Second of all, it shows us that it can be checked in polynomial time, which we show in the paper. And most importantly, for the rest of the talk, it allows us to use flow networks to design voting rules that satisfy GRP. Okay, so the first question we ask is, can we do GRP and Pareto efficiency together? And we answer this affirmatively, and we give a polynomial time algorithm to do so. So this is the most technical part of the paper, and I'll give the algorithm again. Fortunately, yeah, I'll give the algorithm and do my best to get around this lack of flow networks. So the idea is basically that we want to start out with voter weights of 1, and we're going to give a modified version of the network where we just start with no candidates in the network. And we're going to add them 1 by 1. So each candidate has a score that is the sum of the weights of the voters that approve it. And we'll first identify the maximum score and call that S star. So in each round, we're going to add an additional candidate to the network that has score S star. We're then going to basically compute a max flow through the resulting network. We're going to then freeze the weights of any voters who are saturated under that flow, meaning there's K over N flowing through that node. We'll then uniformly increase the unfrozen weights until there's some new candidate that obtains score S star. We'll add them to the network and we'll continue in this fashion. So the termination condition is a little bit abstract, but it has a natural interpretation, but we just are going to stop when there's no way that in the main network, using the flow we have, we could have sent flow to some voter, then to some candidate, then to the sink in an augmenting path of length. And then we'll greedily allocate the remaining probability in descending order of score, and we're done. Okay, so the key part of this to get GRP is the way that we compute max flow. Efficiency follows from basically an argument showing that we are maximizing weighted utilitarian welfare according to the weights at the end of the algorithm.
So
Yes.
what's the score of a candidate? As in like if the candidate is in, say, whatever voters list, you add their weights.
Yes, so it's just the sum of the weights of any voter who approves of that candidate. Yeah, and those weights are dynamic, so their scores are changing. But once a candidate is added, their score will be then fixed at S star essentially, once they're added to the network. Because all the people who approve them will be, their weights are frozen. Or actually, that's not true, sorry. But we kind of work out the kinks when that's not the case, yeah. Okay, so the way that we get GRP is the way that we compute this flow. So the idea is roughly that we have a flow from the previous step, and we're going to then apply for Fulkerson to get some flow that sort of dominates this flow. And there's an issue here, which is that there could be a cycle within the resulting flow where essentially the cycle starts at the source and ends at the source, and the last voter it touches has run out of budget in a sense, so they're saturated. And there's some candidate that's not yet in the network that they approve of. So when we add them later, there's this sort of fairness loss because this voter could have sent money to that candidate, but now they're out. And then this is going to make it so that we don't have a max flow. So we have to resolve this. So we have to identify such a cycle, and then essentially we identify a cycle with a positive bottleneck in the residual network, and then just flow like half that bottleneck, for example, back along the cycle, giving voter I here some of their budget back, meaning they still haven't run out of money. Their weight is now not frozen, so their weight can be used to compute which candidate will come next. Okay, so we'll do that until there's no cycle like that remaining. And this is sort of like an intermediate fairness check to make sure no one runs out of budget before it's strictly necessary. Why is it important? Well, we show that this guarantees that if there is an augmenting path in the main network resulting from this flow, that the shortest such path is of length 3. But then we terminated when there was no augmenting path of length 3, meaning there is no augmenting path when we terminate, and therefore we have max flow, and by our characterization, we have GRP. Okay, so we do a couple of other things. We touch on strategy proofness, which can be obtained with a property called GFS efficiency, or efficiency subject to GFS. In the k=1 case, we show that that is not the case in our setting. So there's this clash with strategy proofness that contrasts with the k=1 setting. And we give a generalization of CUT, which gives both of those properties in the first case, and we use a min cost max flow formulation to do that. Okay, and then in terms of ex post fairness, which is sometimes known as best of both worlds fairness, when you try to achieve both ex ante and ex post. There are some known results here, and we, by drawing a connection to affordability, which is a weakening of priceability, to our flow network formulation, we get this meta theorem, which basically says that any affordable committee, W, can be placed in a lottery where it's in the support, every committee in the support of that lottery, and that lottery satisfies ex ante GRP, and that can be done in polynomial time. So what is the takeaway from this theorem? Well, we can use it to get corollaries that improve both of these results, giving GRP. And critically, it wasn't known previously whether FJR and GFS were compatible. But since GRP is stronger than GFS, we resolve that question. And just note that this blue dotted line is not necessarily wrong. Okay, some interesting questions. Left barrier work, you know, obviously, can we do fractional core in polynomial time? Or if not, maybe something between GRP and fractional core, which would need to go somehow beyond the flow network interpretation. And is strategy proofness compatible with GRP was something we were not able to answer. It's not even known whether strong IFS is compatible with strategy proofness. And then plenty of best of both worlds compatibility questions remain as well, such as ex ante strategy proofness would be an interesting thing to consider as well. Thank you.